over L times A times L. And G recognized that this part is what? Yeah, that's B to the power 2, right? Because that's the magnetic field for a solenoid. It's mu naught N over L times I. So that's B, so it's equal to 1 over 2 mu naught B times, what is this area times length? So that your solenoid has a cross-sectional area A, and it has a length L. That's the volume of your solenoid. Yeah, this is the length of your solenoid, this is the cross-sectional area of your solenoid. And the magnetic field is contained within that solenoid. So that's your volume. Volume. This AL is the volume of your solenoid. Therefore, the energy density, the energy per unit of volume in a magnetic field is 1 over, oh, there is a B squared. This is squared, right? Okay. 2 U naught V squared. This is the energy over volume. For an inductor. You may recall the energy per unit of volume for a capacitor. Recall for a, this is for inductor, right? For inductor. For a capacitor, for a capacitor, recall for capacitor, the energy was stored in the electric field, right? Between the plates, you have an electric field. In an inductor, within the inductor, you have a magnetic field. So for capacitors, it used to be 1/2 of epsilon naught times the electric field squared. That was the energy density in an electric field. Okay. Oh, okay. So that was, this one we got it for a capacitor. We did the same trick. We figured out the electric field. We wrote an expression for the energy was 1/2 CV squared. And we wrote everything in terms of E and divided by the volume, and we got this. Yeah.
So U is energy, but U sub B is energy per volume?
Correct.
Okay.
Yeah. So capital U is just joules. Little u is joules per cubic meter. Joules per cubic. Okay. Have a summary here. LC circuits. Oh, so let me give you the idea of an LC circuit, and the next time I guess we will finish it. I didn't, yeah, time ran out quick. So here's an LC circuit. Here's C, minus minus, plus plus, okay? And you connect your inductor here. What's the current now?
0?
0, there's nothing. The circuit is broken, right? There's nothing. And so we're ready to connect our circuit. So here is a switch, so flip the switch. Close the circuit, what happens? Pluses want to flow. Well, inductor doesn't like that. Why? Well, the current used to be 0, and now it wants to be something, and so it will induce a magnetic field, and so it wants to oppose it. So we will apply the loop rule. We will say the change in voltage across the capacitor plus the change in voltage across the inductor will be 0 over a closed loop. The change in voltage across the capacitor, so the current will be this way, right? What's the potential difference from here to here? It's positive, yeah, it's just, and it's Q over C, right? The charge of the capacitor divided by the capacitance of the capacitor. For the inductor, we said, if you go in the direction of the current, it's minus L times di dt, right? And that should equal to 0. So to solve this equation. It will end up being a simple equation, just some sine or a cosine. Okay, I will stop here, and then next time we'll continue. It's a sine or a cosine because the current is dq dt. So you have the second derivative in q equals to q is proportional to q.
Are you putting close back?